Students, good morning. Today we'll continue the coordination chemistry part 2 under paper 1. So in last classes we have studied the valence bond theory with respect to many number of coordination compounds which explained the type of bonding, and also we have studied the drawbacks or limitations of valence bond theory. Okay, so in order to overcome some of the limitations, the next theory is, say, crystal field theory. The crystal field theory is quite different from that of the valence bond theory. Okay, so now we'll go through the crystal field theory. The main aim or the theme of the crystal field theory is the interaction between the metal and the ligand is purely electrostatic. Okay, electrostatic means ionic in nature. Okay, let us go through the main postulates of this theory. See, the first postulate says that metal ion will be surrounded by a definite number of ligands, and the ligands which must have at least one lone pair of electrons. The second point is, say, the metal ions, they are considered or regarded as positive point charges or positive point groups. And the next one, ligands are regarded as negative point groups or negative charges. If the ligands are neutral in nature, then they are regarded as dipoles, and the negative end of the dipole will be attracted towards the metal ion. And the next postulate is interaction between the metal and the ligand is purely electrostatic. That means it is 100% ionic. And the next one, there is no interaction or overlapping of orbitals of metal and ligand. That means there is no overlapping of orbitals between metal and ligand during the formation of a complex. And now the last one, say, based on the ligand field strength. That means when the ligand approaches the metal ion to form a bond or say interact, so based on that strength, during this interaction, the splitting of d orbital takes place. The splitting of d orbitals takes place. Okay. Now, with this, we'll move on to the next one. Say, the crystal field theory, when it is applied to the different complexes having different geometries. So now, CFT, see, with respect to complexes. Okay. So now the coordination number, if it is 6, then the say geometry is octahedral. If the coordination number 4, that may be tetrahedral or square planar. So you are already well familiar with this. Okay. So now, say the crystal field theory, when it is applied to these complexes having different coordination number or say geometries. So how it explains, we'll see now. Say the metal ion, usually say transition elements, forms a bond or the complex with the ligands. So transition metal ion means which are having partially filled d orbitals. Now the d orbitals which are present in valence shell, d orbitals which are present in valence shell, they play an important role because the d electrons, so okay, the number of d electrons present in the outer shell of the metal ion will interact with the ligand. So okay, now the d orbital, it is nothing but it is a bunch of 5 orbitals. It is a bunch of 5 orbitals. Just you recall, you have studied in previous classes. See here, see the d orbital. It is a bunch of 5 d orbitals. That means they are 5 in numbers: dxy, dyz, dzx, dx square minus y square, and dz square. So if you look at the geometry, that means their orientation in space, say the first three, dxy, dyz, dzx, so which are having double dumbbell shape, and the four lobes are oriented between the respective axis. For example, this is a picture of dxy. That means this is x-axis, this is y-axis. Four lobes are oriented in between x and y axis. Similarly, dyz, dzx. So if you come to the fourth one, it is a dx square minus y square, where lobes are oriented along the x-axis and y-axis. Okay, and the last one is dz square. So this you have to remember. Okay, so before going through the discussion of CFT with respect to say octahedral or tetrahedral or square planar, you have to remember, or you should be able to imagine the orientation of these five orbitals in space. Okay, so now it is quite easy. See the first three where the lobes are oriented in between the axis, and in the next two where lobes are oriented along the axis. In dx square minus y square, there are four lobes, double dumbbell shape, and in the last one it is a dumbbell shape. Only two lobes are there with downward figure. Okay, so this is about the say geometry or the orientation of d orbitals. Okay, now so the 5d orbitals, according to the postulates, metal ion is surrounded by 5d orbitals. See the metal ion. So metal ion, it is surrounded by a definite number of ligands. Okay. Now, say when the ligand field, it is quite away from the metal ion. Okay. So the all the 5d orbitals, when it is quite away from the central metal ion, all the 5d orbitals will be in the same level. That means they are said to be degenerate orbitals. Degenerate orbitals. When the ligand field approaches, which is spherically symmetrical around the metal ion, and it is approaching the central metal ion, so then what happens, due to the interaction of the ligand field with these d orbitals, that means electrons present with the electrons present in the d orbitals, if it is to the same extent, when they are spherically surrounded, all the 5d orbitals are interacting with the same force. So once again, but as a result of interaction, all the 5d energy of all the 5d orbitals is raised. Okay, and further, when the ligands are, okay, they are quite nearer to the metal ion, and they are quite nearer to the metal ion, they are no more spherically symmetrical. That means they are no more uniformly surrounded the metal ion. They are concentrating at particular position around the metal ion. Okay. Now in this way, the spherically symmetrical sphere is now no more. It is a spherically symmetrical sphere which is uniformly distributed around the metal ion so far. But now they are concentrated at particular positions around the metal ion. Okay. So now due to this, when they approach still nearer to the metal ion, the interaction between the d orbitals, that means electrons of d orbitals with the electrons of ligand, will split or will result in splitting of these d orbitals into sets of d orbitals with different energy. So this is, say, suppose in case of octahedral, say this will be the type of splitting. Okay, and this type of splitting due to interaction with the ligands, that means the splitting of d orbitals of the metal ion due to the interaction with the ligand is said to be crystal field splitting. Okay, so now this splitting energy, that means this energy difference, is different in different complexes with different coordination numbers. Okay, so with this we'll discuss in the next class.